So for the end user, truly like the farthest end individual, everything would look exactly the same as it does now, because the entanglement-based key generation that Matt has just been describing would work behind the scenes, providing keys to routers so that they can encrypt messages for all kinds of apps just like they do now, except more securely. Operators, on the other hand, would see some different things. So they would use orchestration, control, and or management software to provision services of entanglement-based key generation, monitor their performance, and resolve any issues that arise. Instead of me waving my arms to explain exactly what this would entail, we can jump to a video that I recorded that shows what this looks like for us here at Aliro. Let's go ahead and watch. To see exactly how that works, let's create an entanglement-based secure communication service. We want a secure connection between the Alice node and the Bob node. So let's call it A to B and specify our first endpoint is Alice and our second endpoint is Bob. Then it asks us for the key buffer in minutes. This lets the operator specify how many keys they want the system to have ready at any given moment. If you have a large buffer of keys, security applications can keep running even in the event of a long outage. This value is expressed as a time rather than a number of keys so that it's easy to plan for real-life situations. For example, let's say we want to provide an uninterrupted flow of a new key every minute to Cisco routers at Alice and at Bob that will keep going for 2 hours even if the quantum system is compromised by an attack or a disaster like a line being cut. For this situation, we would ask for a key buffer of 120 minutes, that's 2 hours, and specify that the key rollover rate is 60 seconds. So that's a new key every minute for fresh security. And click Create. Here in the table, you can see the service we just created. You can click on View to see more information about it, but we're going to go over to the dashboard to look at what's happening on a physical level. The source node here contains a special device that uses a laser and a crystal to generate pairs of entangled photons, and then it sends one of each to Alice here and the other to Bob down here. Receiving these creates an entangled link between Alice and Bob that is used to generate secure keys that were never exposed on the line, but rather created at the endpoints. The sessions in between the source node and Alice and Bob work together to create the service of key generation. If we click on this service that we've created, we can see metrics about how it's performing. So at the top, we have a performance metric showing the proportion of how many keys we've created to how many are needed to meet that key rollover rate. And as we scroll down, we can see plots of different metrics over time. First, we have the key rate, which you can see just jumped up as the system got going. Next, we have the qubit error rate, which is a measurement of the error in the system, which could come from noise on the optical fiber, but it also could come from someone tampering with the line, which we'll see later. But the key thing to remember about this is that we want it to stay under our threshold of 0.08. Because if it does, then our error correction will work nicely so that we'll be able to get a good key rate. And we can also be confident in the security of the system if it stays below this threshold. And lastly, we have the number of keys in the buffer. You can see that when the key rate jumped up, the number of keys in the buffer jumped up as well. So right at this moment, the error correction and protocol steps were performed by Aliros, and we created a block of keys, as you can see here. So one important thing to note is that the number of keys here is not key bits, but rather entire keys, which are 256 bits long each. You can see we jumped up again as we created another block of keys. So everything here is running swimmingly right now. But what would happen if an eavesdropper tampered with the line? By interacting with even a small fraction of the entangled photons traveling on the fiber, the eavesdropper would cause our qubit error rate to rise above that 0.08 threshold, which triggers an alarm and pauses all key generation attempts on that line until the threat has been resolved. Right at this moment, Michelle is on premises at our headquarters, manually tampering with an optical component in the system. So you can think of this like if you had an adversary out there in the wild messing with something, what would happen? How would you know? And the answer is that we'll be able to see our qubit error rate jump up close to the threshold and we get an alarm. So here we have this alarm that we have a high qubit error rate. The QBER has risen above an acceptable threshold. We can acknowledge this and see a representation of it right there on the dashboard. This same error message right there. We can see which service it has to do with. If you have lots of different services going, maybe some of them are fine, but this one has a threat associated with it. And you can also go to the bottom here and see a table of all of your active alerts. If we go over here to the alerts column, the alerts table rather, you can see the specific alert related to this one and you can make logs about it. So I can say Michelle is tampering again. And then you can look at those logs and see exactly what was going on at that time and fix it and update that things have been fixed, etc. And once everything is the way that you want it and you're sure that the threat has been resolved, you can mark it as complete and get back to generating keys. So with that, I'm going to pass it off to Geoff, who's going to show you exactly what we can do with those keys. And he's going to be creating a secure VPN using the keys that we just generated that before this tampering happened. And he's going to be using those keys to send a video over the quantum secured VPN.
Great, thank you, Cara. I'm going to show the process of configuring our two Cisco devices and showing the file transferring across them over the secure IPsec tunnel that was created. So to do that, I will got Alice and Bob's configuration here. I will enable the IPsec tunnel. So there it's on enabled on Alice's side. And that's enabled on Bob's side. You can exit out of here and go back to where we can show configuration. So if we do show crypto skip client statistics, we can see that GET requests occurred. That means it reached out to our skip client on the Cisco side, reached out to a skip server connected directly to our quantum nodes, and that it was able to get keys successfully. Now we can quickly show what interfaces are connected on this device, and we can see there's a tunnel here, a loopback at 0, and a tunnel at 176.123.123. Similarly, on the other side, there's another loopback at 10.10.2020. So if we just ping 10.10.2020 from Alice, we can see that those pings went through successfully. And if we do show crypto IPsec SA, we can see that the tunnel was up and that those packets were sent correctly and that they were all decrypted successfully as well. Now I'll switch gears and move over to our application server, and I'll try to copy a file from its pair application server on Bob app, and I'll do that using a secure copy. So here we can see the copy happening. And then if we go back to the Cisco devices again and do the same, so crypto IPsec SA, we can see there's lots of packets that were encrypted and decrypted and sent across successfully as we were transferring the file across. So that was successfully, and then I will copy that from the application server to my local machine so that we can actually play the video and see it get transferred. Here's a file where it is. So once this finishes, I should be able to click here and see the video play.
And there's the video thumbnail showing up, showing us it's traveled through the quantum secured VPN and we're receiving it on the other side. Every single pixel comprising each moment of this video was encrypted using the keys that we just generated at Alice and Bob via the Untitled link. This is completely different from public key cryptography because we're not simply using math to make keys just appear random enough to keep a certain generation of computers from catching on and seeing the pattern. We are going to the only true source of randomness nature has to offer, the quantum mechanical properties of reality itself. Because of this, we're able to overcome the vulnerabilities of RSA, Diffie-Hellman, and ECC encryption to achieve unparalleled protection against new and emerging threats.